Goyal Brothers Prakashan welcomes all the participants in the webinar. We are happy to introduce Goyal Brothers Prakashan as one of the leading educational publishing houses in India. For more than 6 decades, we have been engaged in the educational publishing and educational technology business. We publish all types of educational books for the K-12 level in different subjects for CBSE, ICSE, and different state boards of India. The company has been selling about 10 million books every year in more than 25,000 schools in India and abroad. Goyal Brothers Prakashan has been conducting seminars, workshops, and webinars for principals, teachers, educationists, students, and parents on various educational and non-educational topics like change in syllabus, exam pattern, career guidance, parenting, pedagogy, coding classes, usage of technology, cyber security, general awareness program, and many more. We have conducted many hundreds of webinars with about 1 million participants in the last 3 years. The technology arm of Goyal Brothers Prakashan, Bright Tutee provides online digital learning content for the K-12 level in a variety of languages for more than 20 educational boards in all of the major subjects.
Good evening to all the participants present here. Goyal Brothers Prakashan would like to welcome you all. We have with us today a senior teacher, subject matter expert, Mr. Shaurya. Sir, you can share your screen and we can begin the webinar now. Over to you.
Thank you, Jatin. I hope everyone can see the shared screen. Good evening, everyone. I welcome you on behalf of Goyal Brothers Prakashan for this webinar, where we intend to deal with how to prepare for the second term or the semester 2 examinations of class 10th in physics. So once again, good evening to all of you. To begin with, let's just first talk about the flow of this presentation. First, I'll give a tentative roadmap from this date till the physics exam, which we have on 9th of May, Monday, 2022. Secondly, we can talk about how to score better, as in like how to get in 90% and more. Some general tricks and tips about examinations. At the later part of the presentation, we'll focus on the syllabus, the bifurcated one, the deleted topics, as well as the important topics in particular units and chapters. And at the last, all your questions are more than welcome. Okay, so to begin with, how do we plan our preparation from this very date today, let's say, till the conduct of our term 2 examination? I'll say some broader aspects out here. First is to pen down and access the current situation. Like if I talk of my subject physics, out of the total units we have for term 2, we'll shortly discuss, how many are we prepared with? Just let's make a note of them. Then of all the things which are left over, let's divide the remaining weeks, which are like around 7 weeks from now to the conduct of examinations, 50, rather more than 50 days, among all the subjects, because it's not just physics you have to go through, right? Now, in this division, you'll take care of few things. Like some subjects like English precisely would only be requiring some reading as well as writing time. Plus, obviously, I'm not just saying that English will not be important for preparation, but I hope you'll all agree that 3 to 4 days might suffice for the entire course of English, even less than that. However, other subjects like mathematics and physics might need greater days. So you need to factor this in, which subject will be requiring how many days. So another aspects to focus on, like physics has numericals, maths has problems. So it takes some considerable amount of time to solve some questions, right? So you need to factor that in as well. Also, how many hours will be required in order to fulfill whatever is left before the scheduled time, that is before our first exam begins on 25th. Now I'll just show you a potential plan how I used to do it when I was a student. I would make a daily calendar where I would take care to mention down the topics. Now, few of us can go through like having 2 hours of 2 to 3 subjects a day. For me, it used to be like one subject per day. I'll get like 5 to 6 days for one subject and get it done with. That is how it used to work with me. But it could totally depend on an individual. What particular thing works best for you, you should go with that. But I'll strongly suggest you pen down a timetable from tomorrow's date till, or rather from today's date till the conduct of your first exam. Now, among your total time or days we have at hand, around 20% should be left for revision. That would be for all the subjects combined. So if I have, let's say, 50 days in hand, 20% of that, that is 10 days, would be specifically left for revision. So I'll make my timetable only for 40 days. I hope it's clear. Now, this is what I'm suggesting, right? Every day, date, and do put a remarks column as well. Because it might be the case like someday something comes up and we could not give the requisite amount of time to that day's curriculum, like the topics that had to be done on a particular day. So rather than marking it completed, we can say like a particular diagram section of house wiring is left, or some numericals related to principle of mixtures and calorimetry is left. Okay, so do it like intensively. This will surely help you. I must re-emphasize here, like this method works. Okay, you will be on track. Like even if I miss the train, that will be just by some. There might be like 1 or 2 topics at worst I leave. Rest I'll be able to cover much in a proper fashion how it is to be covered. Now, some general traits, what could be observed, how to score better overall in any examination, not per se just physics, but any examination we are going to face in our term 2 board ones. First is, will be allotted 10 minutes of reading time before each exam. Now, utilize that time properly in reading the question paper. Okay, read that question paper properly. All the instructions, like among all the sections, how many questions are to be attempted, and figure out these are the questions I'm sure of, and I'll be attempting these. Okay, next, never waste too much time over a question you are stuck with. Let's say you'll not be stuck with a theoretical question, that you'll leave for that matter. But let's say if I start doing a numerical in physics or a maths problem and I get stuck maybe after 2 3 steps, please do not waste time over it. We only have 90 minutes at our hand. Use them really judiciously. Next, as an examiner, I would prefer that the answer script written by students is fairly simple. As in subject like physics, I'm not looking for the beautification of the language you use in your particular answer. What will be more relevant is all the formulas and all the associated diagrams are written in a legible handwriting that are easy to read. So please do not emphasize on writing beautiful English in like maths or science papers. You can stick to rather simple language and give your answer conceptually. Lastly, please manage your 90 minutes properly. You should have a plan, like just before the exams when you solve some model test papers, make it a timed one. Like if it is 90 minutes, go by the clock, like within 90 minutes, I'll pace my paper over section A for let's say 20 minutes and the remaining 70 minutes for the 3 questions to be attempted from section B. So do it properly. Okay. These are some general tips and tricks which would help you to score much better than you previously were scoring. Lastly, few things that can be totally avoided. You must agree there are some students who are right with a book or register in the hands moments before the bell rings for you to enter the hall. You can totally avoid it. It only leads to anxiety, and that is not at all good for good marks. Trust me. Be relaxed. It might be easier said than done, but try to totally calm down before an examination. Do not even study too late the night before the examination, the immediate night before the examination. Prior to that, you might have a working schedule that works best for you in the night. There is less noise, less disturbance, obviously. So few students might find it much more fruitful to study during night hours. That is completely okay. Because as a student, you just need to take out those study hours from your given 24 hours. It really doesn't matter that comes from the day part or from the night part, right? But just before the night, we are going to face an exam. Please do not over cram it. Leave it. How much we know is good enough. Next is, do not talk much with your friends the very night before your exam. How much syllabus have you covered or how much I have covered? Let it be. Because talking too much a night before only leads to some chaos and confusion. Somebody might totally disagree with you on an answer and you might get confused even if you were to know the correct answer. So avoid that. Also, do not read much newer text as in a fresh source on a particular topic from internet or a new book. Whatever you have priorly read, just reinforce that. Do not jump to new text at the last time. And last but not the least, never be late for an examination. That really adds to the anxiety. So always be at your center well before the time. You'll see that will help you calm down a lot. Okay. Having said all this, we can move to the more formal part of this webinar. We already know we are done with term 1 examination, and the entire schedule for this year was to break the entire structure into 2 terms. So we are done with term 1, where we have already done a 40 marks theoretical paper that comprised of multiple choice questions. And now we are here for term 2 examinations, which is a subjective examination, as you all must be already aware of, right? It is a totally subjective paper. Again, the remaining 10 marks, that would be your internal assessment of the practicals, where you would be assigned some projects and you are asked to keep a practical file for the same. Now, I'll straight away just focus on the semester 2 syllabus. Some part of this unit sound, that is a simple single chapter divided into 3 parts in our textbooks. The first one, which dealt with reflection of sounds, echoes, and the problems, numericals based on that, that has already been covered in semester 1. So now there is no need to read this again. It will not be covered in semester 2. Rather, whatever we have done in semester 1 is not a part of semester 2 anymore. So the only units we are left at hand for semester 2 preparation are sound. The remaining parts which deals with natural and damped oscillations, resonance, and lastly the characteristics and nature of sound, that would include loudness and other topics, pitch, etc. The next unit is the core of the syllabus, what I should say, electricity and magnetism. We'll discuss about it in detail, followed by heat, which is again a single chapter, and lastly modern physics, dealing with your radiations, electromagnetic radiations, and alpha, beta, all that. Now, turn by turn, I'll move down the units, telling you about some important topics from where you can definitely expect questions in your forthcoming examinations. Also, the topics written in red color features the deleted topics, like those are definitely not to be covered anymore. So the topics in blue are the recommended important topics where you can just lay some more time over them, get it written a few more times for additional practice. And the ones in red color are the deleted topics. So as we can see in sound, part A has already been covered, and remaining part B topics are free and natural vibrations, damped vibrations, forced vibrations, and then the phenomena of resonance and examples of resonance. You might expect a 1 marker or a conceptual question on resonance. Further, there's one topic I'll ask you to emphasize in this particular unit of sound, that is characteristics of sound and its properties. That is, as in like loudness, that depends on the amplitude. It is only that we have to cover the qualitative part, not the quantitative part. And by this I mean like the mathematical part, like the log graphs for decibels and loudness, those are to be left out. Only theoretical part has to be covered. So next characteristic we read about is pitch, that depends on the frequency of sound, and lastly about the third property as well. Now in the next unit, it's a huge unit, as I already said priorly. Bulk of our paper in the last webinar, we discussed about the exact weightage of each unit. So almost about 50% of our paper depends on this entire unit of electromagnetism. I'm talking about the entire unit, which has like 3 chapters within it. The first part of it is current electricity, which is further divided into 2 parts in textbooks. The first part A deals with the concepts of charge, electric current, potential, and the potential difference. We next move on to concept of resistance. On the properties it depends upon, we basically use numericals on R is equal to rho L by A. And then we talk about Ohm's law. So again here from Ohm's law, the graph could be important. We might have a simple question on graph between a voltage and current passing through a conductor, and we may be asked to find the resistance that we know can be found using the slope of a VI graph. Now in this, since we are talking about this, I should just point out a mistake students commonly do. If it happens to be a IV graph, that is I is along the y-axis and voltage is along the x-axis, then the slope of the graph will not give us resistance, rather it will give us the conductance, that is reciprocal of resistance. Why? Because the slope is y upon x. So if I have current on my y-axis and potential difference of voltage on my x-axis, it will give me 1 upon r, because I by V is 1 upon r. Okay, moving ahead, we have last topics in part A, which are ohmic and non-ohmic conductors. And lastly, we talk about the resistivity of a conductor, which is also called as specific resistance. Again, the last topic has been deleted. Even the earlier topic, the way we experimentally show how to the experimental circuit setup, how to verify Ohm's law, has been chucked off the syllabus. Okay, and the part B basically includes talking about EMF, that is electromotive force. Again, this name is very disguising. It is not at all a force, it's basically the work done. Next topics, again, this is all related to an electric cell, right? Terminal voltage, internal resistance of a cell, and the potential difference across a cell. So you only have basically one formula here, that EMF E is equal to V plus IR. That is all what is there in this particular part. Lastly, the important part of this particular chapter is circuits based on the series and parallel combination of resistors. So definitely this is a question to come, right? Among the section B, will shortly discuss the format of the question paper. We can surely expect a circuit based question to be coming in the forthcoming examinations. Moving to the next chapter under this unit 4, electromagnetism. It is based on electric power and household circuits. Again, this is a huge chapter divided into 3 parts. I have just pointed out some topics which are potentially important, I would say. To begin with, in part B, we have the ring structure, the diagram, the block diagram becomes an important question which might come. As in part A, we can definitely expect simple numericals based on the bill calculation, that is the electricity bill calculation of a month, given the appliances are running for these many hours of these much power ratings, right? So we have done such types of questions a lot, I guess. Next, in part C, again, we talk about fuse and switch safety devices, earthing, 3-pin plug and socket, and color coding of wires. Mostly theoretical topic, but yeah, fuse and switch, again, their diagrams and workings may come in your exam as a sub part of a part B question. Moving ahead to the last chapter under this unit is electromagnetism. Potentially, I'll say the most conceptual chapter in your entire term 2 syllabus, the most where you actually need to apply yourself to solve the questions. So in part A, we begin with Oersted's experiment, that is basically the birth of magnetism, as we say in physics. The magnetic field and field lines becomes an important topic, further to be followed by Maxwell's right-hand rule. We'll talk more about these here. I'll take some time. Now, as a student, you might have whole lot of problems how to distinguish where to use which particular rule. I, for once, will try to make this absolutely clear in a question we discuss later. So all these 3 rules I've already highlighted. We are definitely expecting questions of this, definitely. That is right-hand Maxwell's rule and Fleming's left and right-hand rule. Now, these are 3 different rules which we'll shortly discuss where to use exactly. Now you can also see all the red topics, and there is a lot which have been removed from the syllabus. Those would be the magnetic field produced due to a solenoid, the DC motor, Lenz's law, that is to determine the direction of induced current, AC generator, and lastly transformers also have been removed. Moving to the next unit, heat, that is our 3rd unit for this term 2. In the part A, the calorimeter, as in the construction or as an apparatus, how it looks in the diagram, that all have been removed. Further, the measurement of specific heat of solid, a small topic in this chapter, also has been removed. Now we are definitely expecting another question from here, a 3 or 4 marker question, numerical, on the principle of calorimetry, or as we say sometimes, principle of mixtures. So we might discuss this also today, one question or two maybe. In the second part, we talk most about the change of phase, that is latent heat of fusion and vaporization mostly constituted this topic, but again latent heat of vaporization, that is the calculation of heat required to go from liquid to gaseous state or vice versa has been removed. So we are only expecting numericals restricted to latent heat of fusion, that will be going from solid to liquid or liquid to solid state. Now, our last unit, which is a part of our term 2 syllabus, is modern physics. Again, there were two parts. One is totally removed. What is important out here is structure of atoms and nucleus, radioactivity, the three types of radioactive radiations, namely alpha, beta, and gamma radiations, their nature, properties, and examples. This, we are definitely expecting a maybe conceptual question from this, or maybe a theoretical 2-marker question from the one of the radiations. Okay, so I hope I have properly covered the next syllabus that is coming for term 2. We have specifically dealt with the important topics as well as with the deleted portions of the syllabus for term 2 examinations. Now, let's lay our eyes on the specimen question paper released by the board. ICSE, about a month before, released the specimen question paper, which will be the exact pattern of which you are going to face all the exams. So the physics paper particularly is a 40 marks, like many others. As previously mentioned, you'll be given a 10-minute reading time. Now let's re-emphasize what this is meant for. You'll see that 15 questions in your question paper. The part A is totally mandatory, so don't see that. Use this 10 minutes only to read through part B. Do not waste a single minute reading through any multiple choice questions which we have part A, because at the end of the day we have to attempt those. There's no choice. Specifically use this time to figure out among the 5 subjective questions, which further have 3 subparts each, which 3 questions should I attempt? That means among the 15 questions I have in part B, which 9 will I be able to answer with accuracy? Now, I'll strongly suggest our term 2 curriculum doesn't have very tough numericals. There are very less concepts, and if you can master them, I always advise my students to go for numericals. Always. That will save you time and that will guarantee you full marks if you do it correctly. Instead, if you do a theoretical question, you always have a scope of some deduction of marks. I hope you get this, right? So always opt for numericals. If you know that particular topic well, go for it. It will save you time and fetch you complete marks. Okay. So I almost talked through it. Your entire question paper will be allotted to you for 90 minutes of writing time, which again is broadly divided into 2 sections, section A and section B. Now, among the 40 marks for your paper, 10 marks you have in section A. Those comprises of 10 multiple choice questions. Something you have been really familiar with of late, right? So you know what to do there. A, B, C, D, no negative marking. Even if we don't know, we cannot leave a option or a question unattempted. We at least need to put in a guess, right? We have a decent 25% probability to be correct in that question as well. So first section comprises of 10 1-marker multiple choice questions where only one option would be correct. There is a typo error. Section B comprises of the remaining 30 marks. Now it has 5 subjective questions, and it's not just one question of 10 marks. It's basically a question broken down into 3 different questions. Okay, I'll repeat this. Every question in part B is of 10 marks, but it's actually broken down into 3 different questions, which would roughly be of 3, 3, and 4 marks respectively. So 3 plus 3 plus 4 will add up to 10 marks of one question that we are talking about in section B. So among the 5 subjective questions, we have to do 3. Now we cannot have external choices. We do 2 subparts of question 1 and the third subpart of question 2 maybe. No, that is not allowed. As a whole, I'll have to pick 3 questions. That means all the 3 subparts of the 3 attempted questions out of given 5. So I hope I have made this marking scheme or the format of the question paper absolutely clear to all the teachers and students. Now, this is the official website, the link from where you can directly download the specimen question paper. I've taken time to have some snaps out of the questions which I'd like to discuss with you. So let's start with the first question we had in our specimen question paper. It was again a section B question and a sub part of a question, but you can see as it's of 3 marks, which further is basically 2 questions. First thing says calculate specific heat capacity of water, and the second is heat release in the region BC. Let's just discuss a couple of questions out. So the question says the diagram shown below is a cooling curve for 200 grams of water. The heat is extracted at a constant rate, that word should have been there, constant rate of 100 joule per second. So this is a totally conceptual based question. The topic obviously is heat, and the concept to be used out here is principle of calorimetry, right? So we have a basic formula in calorimetry that Q, if it is represented heat, is equal to mass of the substance multiplied by specific heat, which I am denoting by small c, multiplied by delta T, that is the change in temperature. So we know this, right? The heat gained or heat lost by a substance of mass m with specific heat capacity C overgoing a temperature change of delta T. So delta T could be both, right? Positive as well as negative. That will depend, since the heat is being taken in an object, if the temperature increases, and if the heat is being lost by an object, then obviously the temperature is decreasing, right? So let's now put our eyes across this graph. From A to B, we see a straight line and it is a decreasing or a negative slope, as we say. So what it tells me, in the first 640 seconds, right? That is 10 minutes 40 seconds, the object is constantly losing heat at a rate of 100 joule per second. So first thing we can clearly figure out is Q from the region A to B is 100 joules into how many seconds? 640 seconds. So we know it is 64,000 joules of energy that is being lost by the object as we travel on our graph from A to B. That is the first part of the graph. In the next part, although we see that the temperature part, that it is at a constant temperature 0 degrees Celsius, but still it is losing heat as said in the question at a constant rate of 100 joule per second. So the net heat lost from B to C would be the time 100 joule into the time, that is 1312 minus 640 seconds. So from the 640th second to the 1312 second, we calculate how much time was there, and we again multiply it with the rate of 10 joule per second. So you can always check things dimensionally, since it is 100 joule per second and we are multiplying it with time. So obviously we are getting a quantity which units is joule. So obviously it is correct. We are getting Q. So again, if we do the subtraction, it's 672 multiplied by 100 joules. This is the amount of heat that the object lost going from B to C on the graph. Now again, coming back to the original or the first part of this graph, that is going from point A to point B, the heat lost is 64,000 joules. We have already been given the mass of the object, which is in grams. So always remember the first thumb rule of physics, always do your numericals in SI units. So this mass out here becomes 0.2 kg, that is 200 divided by 1000. C is something we have been asked to find. We have been asked to find the specific heat capacity of water. And delta T, as we can infer from a graph, as the object goes from A to B, the temperature decreases from 80 degrees Celsius to 0 degrees Celsius. So this delta T's value we have been given 80 minus 0 is again 80. So there were 4 parameters in this particular equation. Q is equal to MC delta 2. We have figured out what is Q. We know delta T. We know M. I guess everybody can calculate C, that is C would simply be equal to Q upon M into delta T. Do the maths, right? Again, if you have any doubt over the unit of C, do not remember it. We can strictly write it from here. Q's unit is joule. For mass, we have kg, and for temperature, we have the SI unit degree Kelvin. So we got the unit of C as well. Besides the numerical value, your answer must contain the appropriate SI unit for the requisite physical quantity. Out here it is joule per kg per degree Kelvin. Now in the second part, it is asked how much is the heat released in the region BC. We have already calculated out there, right? Now there might have been a theoretical question to be discussed here. Like even if an object is losing heat as it moves from point B to point C, how is it possible that it stays at a constant temperature of 0 degrees Celsius? Now this is the concept of change of phase of a substance. And what is exactly happening from B to C? Although it is constantly losing heat, but without a change in temperature, that is, it stays at 0 degree, signifies that water is changing its state from liquid to solid. That is, it is converting from water to ice as we move from B to C on the graph. So I hope this question is clear. I can talk about the next question. So before we move ahead, this concept should be clear. We are definitely having question on this, that for a change in temperature of an object of mass m with specific heat capacity C, this is a simple formula to calculate the heat lost or heat gained. Next, I'll take time to discuss, as I was talking about, the three rules we have, right? The right hand thumb rule, left hand rules. So there are three rules to be clear with. First is Maxwell's rules. The name is not important. What is important? Where to use what? Fleming's left hand rule. And finally, the third one is Fleming's right hand rule. Now, first rule, Fleming's right hand rule is for finding the direction of current in a conductor if the magnetic field lines are known to us, as in pictorially, or the vice versa case. If we know the direction of current, we can draw or sketch the magnetic lines. Let's take a quick example. Let's say I have a straight current carrying conductor with this arrow signifying the direction of current I. Now, right hand rule says it can again be used both ways. So firstly, never confuse between your right and left hand. That is something you need to be absolutely clear about. Never confuse between your right and left hand. So as we are seeing the screen, there might be lateral inversion, right? So this happens to be my right hand. Now, first rule says always use it like a thumbs up position, right? This is exactly the logo of thumbs up. So this thumb could work as one of the quantities. And what are the two quantities we have in first rule? It is either current or the another quantity is magnetic field. Just two things. There is no third thing in this rule. So if my direction of my thumb, that is a straight direction, represents current, so this swirl of the fingers around it gives the direction of magnetic field. If you could all do it with me, just use your right hand thumb and keep it like this I have in front of me. Now, as you will see that your thumb is pointing towards the roof of your room. And if you notice, the swirl or the curl of the fingers, as you see it, is anti-clockwise. Try it now. It is anti-clockwise, right? So if I have a current carrying conductor, which is a straight current carrying conductor, I must lay emphasis, because this thumb is a straight line. So this around a straight line will always have magnetic fields, which is going anti-clockwise. Anti-clockwise. So this helped me find the direction of magnetic field around the current carrying conductor, right? We, I guess, are clear about the fact that magnetism ka source is current moving across a conductor. Secondly, it can be used ki what if my wire now is a circular or a curved path? Let's say I have a wire in which current is now flowing in an anti-clockwise sense. So this time, again, I am changing a thing. As I said, it works both ways. Last time I took thumb to be the direction of my current, and this fingers gave me the direction of magnetic field. Now instead, in the second case, I see I cannot use my thumb for the direction of current. Why? Because it's not a straight wire, it's rather a curved, in this case a circular loop. So let's now use the curl of the fingers along the direction of current. As I'm doing right now, I am moving along the direction of the current traveling in the circular loop, that is anti-clockwise. So this time this curl of my fingers were chosen for current. So the another thing out there, that is the thumb, gives the direction of magnetic field. So out here, if it is moving like this, I'll represent my magnetic field with a dot. That means if my current carrying loop is in the plane of the paper in front of me, the magnetic field is coming out of the paper. It's a three-dimensional thing, right? I cannot show that. It's like coming out of the paper. If we instead use a cross, if we want to show anything is moving into the plane of the paper. These are like two conventions, or let's say nomenclature we use for representing directions perpendicular to the plane of the paper in which we are writing our answer scripts. So I hope the first rule is clear, right? There are just two things to be talked about, that is current and magnetic field. Let's talk about the second rule, that is Fleming's left hand rule, where it has to be put to use. Now, Fleming's left hand rule is for finding mostly the force on a current carrying conductor when placed in an external magnetic field. Now, this word out here, external, is important. Why? Because by definition, the current flowing in the conductor automatically produces its own magnetic field. So you should never be confused. We totally are not talking about that magnetic field which is being produced by the current flowing through a conductor. We totally neglect it. What we do instead is we talk of an external magnetic field. As you can see in this question, it says, find the direction of the force felt on the conductor AB if the direction of current passing through it is from A to B. So we should always put an arrow. This is the direction of current in the conductor on which the force has to be computed. Now this current carrying conductor happens to be placed between two magnets, as we can see. It could have been a single horseshoe magnet. There is no issue. It could have been a single horseshoe magnet. Now we already know, like, the magnetic field lines, or the direction of magnetic field, is always from the north pole towards the south pole, as can be seen in the figure itself. So all the arrows moving towards your right signify the direction of magnetic field. Now we can talk about this left hand rule. Now there are three quantities involved here. First is force, second is magnetic field, and third is current. So I normally remember, or ask my students to remember it by the American detective agency FBI. So let's catch hold of our left hand. Try to orient your thumb and the first finger with the second finger like the three-dimensional coordinate axis, x, y, z axis. That means they all should be perpendicular to each other. You can see for yourself. This finger is perpendicular to thumb. This thumb is perpendicular to my second finger. These two fingers are also perpendicular to each other. So simple three-dimensional coordinate axis. This is the same format even for the third Fleming's right hand rule. The idea is same, how we need to keep our hand such that all the two fingers with the thumb are perpendicular to each other. Now we should be flexible with our wrist. We can move it anywhere. But in moving my wrist, I should never change the orientation of my first and second finger along with my thumb. Whatever I do, I'll not change these. They have to stay fixed. They will not move. So just practice this. Keeping your first thumb and two fingers straight and moving your wrist as it is required. So let's now jump to the rule. FBI. Start from here. F, B, I. Thumb is always F. First finger is B, and the second or the middle finger is your current, I. So there are three quantities in picture here: the force, the magnetic field, and the current. Again, to re-emphasize, this B is, or rather has nothing to do with the magnetic field produced by the current carrying conductor. I'm totally neglecting it. If I were to draw, you can see for yourself that the magnetic field actually would have been produced in spirals around this. So I'm totally neglecting this magnetic field produced by this current carrying conductor. Thus, I use the word external magnetic field that has been produced by these two magnets, or maybe one horseshoe magnet. Let's now talk about the question. B is in this direction as per my figure. So B is in this direction according to my figure. So first thing, catch hold of one quantity. I took B first. You could have equally taken K. I know the direction of current. First, let's try to put my second finger along the direction of current. Doesn't matter where you start. I started with magnetic field. Key one quantity I know, magnetic field goes from north to south. I have pointed my first finger along that direction. Next, what I could do, keeping this same, I can still move my hand like this. You get it? The direction of B is not changing if I move my hand like this. However, I move like this, the direction of B is changing. That I cannot do. So B keeping fixed, I can move this. Now I'll try to orient my second finger along the direction of current. That happens to be like this. You can try it for your figure right now. So once you have achieved this, your first finger is along the magnetic field, your second finger is along the direction of current. The thumb will give you the direction of force felt on the current carrying conductor. So in this case, B was along this. I was potentially coming out of the plane of paper. So this is 90 degree. So this, So this perpendicular, my thumb gave you the direction of magnetic field. So I hope the second rule is also clear to you all. That was basically this question. So my answer out here would have been up. This is the direction that this current carrying conductor will feel some force on. That is in the upward direction. I hope it's clear, right? The third rule, guys, out here is for electromagnetic induction. That is totally another topic, right? It says that a changing magnetic flux can induce potential difference across a across a conductor. So in simple understanding, I teach my students, do not get confused. Use a similar concept, FBI out here also with the right hand rule. Now what it is, F, let's call it now motion. A scenario where let's say I have a conductor, let's say a piece of rod. There is no current that is running in this conductor. That is EMI. Please be very clear of this. The idea of EMI is that I only have a conductor and maybe I have some magnetic field that is going into the paper. So perpendicular to the orientation in which this conductor is kept. Now, if I happen to move this conductor towards right, I'll say that some current will start running in this conductor had this circuit been complete. If it is not complete, I'll say there will be some potential difference or normally voltage as we call it across the length of the conductor. There will be some potential difference between these ends. It will more like start acting as a cell battery. So out here, F should stand for motion. जिस direction में force है, motion वही होता है. B is again magnetic field, and thirdly, I is current. So normally, Fleming's right hand rule is used in electromagnetic induction to find the direction of the induced current. Let's apply it to the given situation. So again, I'll have to use my right hand rule now. Again, FBI, same technique. I know firstly, again, I am starting with magnetic field. The magnetic field is into the paper. I pointed my first finger along the paper. Now motion, that is force, is along this direction. So keeping the direction of the magnetic field same, I pointed my thumb in the right direction. That is the direction of motion of the rod. Now my second finger is this pointing upwards. So I know if current was to flow across this conductor, it would flow in opposite this upward direction. I guess I should repeat this. Same technique, putting the first thumb and two fingers of my right hand such that they form three axes of three-dimensional Cartesian coordinates. Again, first thumb stands for force, that is motion, in which the direction the conductor is moving, motion. First finger is magnetic field and third is current. So magnetic field is into the paper, motion is thumb is towards right, that is rod is moving towards right. The current should flow in the upward direction. As I pointed out, the current will only flow if the circuit is complete. Had this wire been broken, I'll say current will not flow, but the potential difference will be such that this point is plus and this point is minus. This is EMI, where and how we use our Fleming's right hand rule. So I hope I was able to bring some clarity with you all students out here. Lastly, we are definitely expecting a circuit-based questions, which will be fairly simple. I guess probably having maximum 3 to 4 resistors, not more than that. So it's a potentially very simple question. Let's just quickly take it. Let's say I have a cell of 12 volt. There are 3 resistors in this particular order, and you have been asked to find the value of the ammeter or the reading of the ammeter as well as the voltmeter. Now, one thing you all should be clear, ammeter is always connected in series, however, voltmeter is to always be connected in parallel. So first thing what I always suggest is make the circuit simpler in stages. First thing what should I have done is keeping the 2 ohm resistor like that. We can easily see that this 4 and 4 ohm resistor were in parallel, and two like resistors being in parallel, the net resistance will be half of it. So I, without solving or using this formula 1 by R is equal to 1 by R1 plus 1 by R2, I already know since R1 and R2 are equal, this R will simply be equal to R1 or R2 by 2. So 4 ka divided by 2 is 2 ohm. So I have just substituted these two resistors with a single resistor, and I'll carry on with my circuit. This was the orientation of my circuit. Lastly, what I would change this to two resistors in series. It is one single resistor of 4 ohm, 2 plus 2, and again the cell of 12 volt. This is how you should always approach a circuit question. Simplify the circuit into stages from 3 to 2 resistors and finally to one single resistor. So without even knowing the question, I found few things. The net resistance of my circuit is 4 ohms. Once I have the net resistance, the next thing I automatically have is the net current that starts from the battery. So it is 12 divided by 4, that is 3 volts. Fair enough? So sorry, my bad. 3 amperes, it is current that we have taken out. Now we know that from the battery always a 3 ampere current starts. So out here it is 3. So first answer I have got. By the time it reaches my ampere, it was still 3 ampere. Done. Now this is the first junction in my circuit. Junction as in the point where a current gets the opportunity to divide. It's simply like water flowing and achanak there are two tributaries for a river. Some of the part of the water will go there, some will go here. Now it should be absolutely clear it will not always be equal distribution. If there was 3 ampere current coming from here and there are two paths, it is not always the case that 1.5 and 1.5, that is current, would divide equally among the two given paths. It only and only depends the resistance of each path. Out here, it's a simple question. Both the paths where the current split had a resistance of 4 ohms each. So without any solving, I know for sure that out here, 1.5 ampere current will go via the upper 4 ohm resistor, and the remaining 1.5 ampere current will flow through the lower 4 ohm resistor. But again, let me emphasize, it is only because these resistances were equal. Else I cannot figure out this without in a similar fashion that it will be equally divided. So we know the current passing through these resistors, we know the resistance. So I know I know R, so I can find the value of this voltmeter, that is according to Ohm's law, IR should be 1.5 into 4, that is simply 6. Just a minute. 6 volt, yeah, 6 volts. So I've got my second answer, 6 volt. So if I see that in this circuit, 6 volt was dropped across this combination of two resistors in parallel, the remaining 6 volt must have been dropped across this resistor. So had there been a voltmeter out here also, I would know for sure that 12 minus 6, this will be 6. So this is another important topic for your term 2 examinations. I hope you will take care of it. So I hope I was able to clear your some doubts, which I think potentially are the most important topics: circuits, principle of mixtures, and your all the three rules, that is electromagnetism. Just lastly, to wind it up, I'll again just emphasize on few things where you focus. We are not in a habit of writing of late, right? We have been only dealing with multiple choice questions. So I'll strongly suggest everyone, whatever you're doing, reading even the theoretical questions, what is electromagnetic induction per se, please write those answers. Do not just read it and think you'll be able to write it on the exam. Maybe few of you are able to, but I'll strongly suggest you write each theoretical aspect of your syllabus multiple times, precisely twice or thrice, so that on the day of examination, the thinking part or the wastage of time there is less. Your hand as a motor skill knows that this is the answer, let's start writing it. There is absolutely no wastage in time on this. Secondly, as I was trying to emphasize so much here, please concentrate on the numericals: heat, the electric household bill, that is a simple example I didn't discuss, circuits, and all the rules we just discussed. These are literally important for your forthcoming examinations, and having mastered these concepts, I can assure you with a proper timetable and mastery over these concepts, you are bound to score more than 90% marks in your physics paper. So I wish all of you all the best. We already have done a webinar priorly on the question bank Goel Brothers released. It was dedicatedly having all the summary of the requisite topics, and most importantly, it had the model test papers, which are a must before you appear for any examination. This will give you a hang or a particular place where you are in a subject. Okay, so kindly attempt these in a proper manner, that is time-based manner. 90 minutes proper. You will not get up for washroom or drinking water or that matter. Okay, attempt it like a proper examination. Okay, now I would like to encourage any doubts or suggestions if I may have.
Yes, sir. We'll take the doubts now. Sorry, sir. Can you hear me?
Yes, yes.
Yes. Sir, I have also shared the link of the book where they can see the book, complete book.
Yeah, it's already there on my screen as well.
Yeah, so participants can check this link and see all the books. It includes physics and all other subjects as well. Thank you. So we are open for doubts now.
If at all you have doubts, I guess you cannot be unmuted, so you can just type in your doubts.
Yeah, we will be taking doubts on chat box, sir. Anybody?
Yes, ready, sir. Raise your hand. Could you please type in your doubts, sir? That will be really helpful.
Good evening, sir.
Good evening.
Sir, can we expect 4 marks question?
Yes, yes. As I said, among your part B, each 10 marks question, where we have to attempt any 3 10-marker questions out of the given 5, those 10-marker questions are split into 3 subparts. That would be of 3, 3, and 4 respectively. Now, again, that 4 marker still can have 2 subparts of 1 and 3 weightage or 2, 2 weightage. But yes, we can expect a 4 marker single question on a circuit with 2 or 3 subparts. Like in a given circuit, the one which we did can come as a 4 marker question for sure.
Sir, one question is Lenz's law is deducted or not?
Yes, Lenz's law. Okay, I have some doubts, per se. So Lenz's law, as I already showed, has been removed from our syllabus. So we will not teach exactly Lenz's law. That is the concept of the nature does not like the change in magnetic flux. That part, the theoretical version, how to find the direction of induced current in EMI using that has been removed. So the only thing we are left with is Fleming's right hand rule as to find the direction of induced current in electromagnetic induction. Okay, I have a doubt. Like I had a doubt. We students we just ignore numericals, so to avoid, what should we do? Okay, I guess I got that. I personally thought if you attempt numericals, it's an easier way to score complete marks. But if at all you do not master a concept, it will be definitely better to avoid numericals and go with theoretical questions which you have as an option. So that is what I said, the 10 minutes time you have as your reading time, put it back to reading of your section B questions. Figure out out of the 5 questions with the respective subparts, which 3 questions can I do in greater detail or till most extent. So how will we get the resistance in parallel? I guess you know this. Resistance formula for parallel is 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3, maybe how many resistance you have in parallel. It's an inverse summation formula we have.
Sir, one question is AC motor question is coming or not?
No, DC motor as in the entire setup has been removed from the syllabus.
Right. Another question, sir. Can you say the chapter which has more weightage in the board exam?
As I already discussed, I should not say the chapter wise weightage, but when it comes to unit, this entire unit electromagnetism will constitute around 50% of the paper, which is much, I guess.
Right.
Okay, I'm having a lot of questions in the chats. Is the measurement of specific heat in syllabus? See, measurement of specific heat, as in we obviously can expect questions. One we discussed also, that was from the specimen paper itself. But what was deleted from the syllabus is the specific heat measurement of solids in experiment. That was deleted. How to calculate total resistance when the four resistors are perpendicular to each other? I'm precisely not getting it. You mean four resistors are perpendicular to each other, as in it forms a square. See, resistance can only be found out between 2 points, some starting and end points. So you need to tell me those. Any other questions?
I think, sir, we have covered almost everything. Yeah.
Yeah.
So numerical of latent heat are there.
So sorry.
Numericals of latent heat are there.
Yes, very much. Q is equal to ml. A simple formula is there in our syllabus. So latent heat only of fusion is there. So student might be asked how much heat would be required to take ice or change 200 gram of ice to water, like that.
One doubt is from Smita ma'am. Smita ma'am, you can unmute yourself and speak.
Yeah, good evening, sir. Sir,
Good
my
evening,
doubt
ma'am.
is how to prepare. Actually, the students get the confusion when the numerical will be based upon a specific latent heat of fusion of ice with the water.
Ma'am, I don't know what would be the confusion there, students and teachers for that matter. We know that
little bit students feel little bit confusion. I know I can clear it, but the question from the students, what I faced, the average students are not able to solve that sums. 11A, they are not having any doubt, but 11E, yeah.
If I may suggest, what we can do is, ma'am, we can just make them practice 5 to 10 questions, and we can ask them to, if they do not get a hang of that concept, for them it's a simple mathematical formula that Q is equal to M into L. Now, if there are 3 unknowns and 2 are given to you, you can always find the third one. We might approach this with maybe some average or weaker students.
Okay, sir. Yeah. And one more doubt, sir. If you are going to connect the appliances to the neutral wire, correct?
Could you please pardon, ma'am?
Yeah. If you are going to connect the appliances to the neutral wire,
yes.
When the fuse blows off, does the appliance will work, or how is it? Because the appliance remain connected to the live wire.
Ma'am, but for a circuit to be complete, even if the fuse is blown off, that means neutral wire has gone off. So it will not work, because even if the current is reaching from one wire to an appliance, but the circuit is not getting completed because the return current is not coming back. So an appliance will not work, obviously.
Yeah. Okay. Thank you, sir.
Okay. Jitin, I guess we are done.
Imran sir, please, you can share your doubts. Sir, few more doubts. There are a lot of questions coming in.
Okay.
Yes, good evening, sir.
Good evening, sir. How are you?
I'm fine. How are you all?
Very well, sir.
Just I wanted to ask, since there was a lot of panic situation the first semester, as we all can see, students were really panicked and they are really scared to attempt the physical papers. So what approaches can be made to make them a bit calm and to make them attempt all the questions easily? Since we are practicing with them a lot, since there should be some way to reduce the phobia in them of physical exams. So what suggestion can you give?
Sir, I would say I will not be a master to answer your question, because it's more of a psychological thing. Me being a physics teacher, what you're doing is good enough, sir. You're making them practice the requisite syllabus, the theoretical as well as the numerical part is what I will say is the best you have done, as in subjectively. But from my side, I'll just personally say we can just talk to them. That is the best what we can do to counsel a particular student. Just try to calm them down. Do not worry, it's not a tougher MCQ paper, because that I understand was a new and a tough thing. It was challenging. There was no gray out there, right? It was totally black and white. If you are right, you get marks. If you're wrong, there is 0.
Exactly.
So we can just try and put it into their heads. It's a normal affair, one which you have been used to 2 years back. So even if we do not get complete marks, if we write the necessary formula or the related things, according to the marking scheme, you'll not get a 0 out of 3. You'll have some marks to you.
Okay.
So we might try to just calm them down, console them. It will be a relatively easier affair this time.
So the paper pattern as we have in lots of specimen paper, it will be same, right? 3 sets to be attempted from the compulsory part.
Yes, sir. That
yes, exactly.
as far as the specimen question paper is, the question paper we expect would be exactly of the same format.
Okay, okay. Thank you, sir. Thanks for.
Thank you, sir. Good evening.
Right. Thank you, sir. I think we have taken almost all the doubts and we are over the time now. We will have to wind up now. Yeah. Thank you so much for all the participants who were present here. And special thanks to you, sir. It was a wonderful session. All the students are still here. Everybody, I think, enjoyed this session. So with this, we'll end the program today and come back with the next session tomorrow.
Thank you so much. I hope it was something to learn for everyone, even myself. Have a great time ahead. All the best, students, for your examination. All the best. Thank you.
Thank you.